Okay, so last time we learned about how to go back and forth between Cartesian and polar coordinates. Now we're going to do the same for equations. And we're going to start with rewriting Cartesian equations as polar equations. Because up to now in math, we've only worked with Cartesian equations. That's all we have. But some of them, we learned in pre-cal last semester, don't look very pretty when we write them in Cartesian coordinates. Things like circles and ovals kind of looked ugly when we had them in Cartesian form because they are closed curves. They are round. And a straight line grid is not good at capturing round things. So those equations that were difficult to write neatly in Cartesian form will often look prettier in polar. And that's why we want to be able to write them that way. There is a three-step process. Yeah. The first, we are going to substitute. Second, we are going to simplify. And then we are going to solve. 3 S's. Simplify, substitute, simplify, solve. Substitute, simplify, solve. Very similar process going the other way. Substitute, simplify, solve. What we are doing in the equation for the very first step is we want to replace x and y with the things that x and y are equal to. And you just practice that. We know x is r times cosine theta. Y is r times sine theta. You are going to make those substitutions into the equation. Everywhere you see an x, replace it with parentheses r cosine theta. Yeah? Once you've done that, you are probably going to get an expression that's kind of ugly. It's going to have squareds in it and fractions maybe. So the next step is to make it pretty. You want to simplify. Yeah? Reduce where you can. Yeah. Combine any like terms that you see floating around. And because we know that there are relationships between sine and cos, oftentimes you're going to use trig identities. Because if my equation has both x's and y's, it's going to have both sines and cosines. And so sometimes those trig identities that we learned in the last chapter are going to help us make our expression more simple. Yeah. Last step, just like we typically in Cartesian form want our equation to be y equals some stuff with x in it, for polar we want it to be r equals some stuff with theta in it. So we want to solve for r. Get r by itself. Substitute, simplify, solve. We're going to do a couple examples. You can see what this looks like. Yeah? We want to write x squared plus y squared equals 9 in polar form. I sincerely hope we're not watching videos on our phone and we are, in fact, listening and taking notes at that back corner table. I can. We've seen the equation like that. We saw it fairly early last semester when we talked about pre-cal and we learned about our families of functions. This guy's going to get prettier when we rewrite him. We're going to use these steps. So first step is substitute. Replace x and y with the things they're equal to. So this equation is going to become whatever x is squared plus whatever y is squared equals 9. And Nicholas, what is x equal to?
X equals what?
That's my question. When I do my substitution, what do I replace x with? Oh, no. Arlene, can you help Nick out? What is x equal to? We wrote it down at the substitute step. Brownie face. Nobody taking notes today? Louder, Paul. Thank you, r cosine theta. I'm glad somebody is awake today. Same thing for the y. Y is r sine theta. Step 1 is done. I have substituted. Yay. Next step is to simplify. I see a cosine squared and an r squared floating around, and I know those have a trig identity. So first thing I'm going to do is separate those parentheses by distributing that exponent through. R cos squared is r squared cos squared. Second term is going to become r squared sine squared. And looking at those two terms, r squared cos squared, r squared sine squared, what do they have in common? R, yeah, you got squares in there. Square. Pull out that r squared they have in common. If I take the r squared off the first term, I'm left with just a cos squared. If I take the r squared off the second term, I'm just left with the sine squared. So r squared times cos squared plus sine squared equals 9. And I spy a trig identity up there. Cos squared plus sine squared, what is that equal to? First trig identity of the course. 1. Gold star for Alexis. Very good. This whole thing is equal to 1. And r squared times 1 is r squared, right? Anything times 1 is itself. So this is just, that should not be in red. Try that again. R squared equals 9. It's not bad. 2 lines. And I've done the simplifying. That's as simple as it's going to get. Last step is to solve for r, not for r squared. So last step, I need to undo the square with a square root. On the left, I get r. Check, that's what I wanted. On the right, when I take the square root of a number, what do I pick up in front? Plus or minus. Very good. I can have a positive or a negative solution. The fact that I got 2 numbers tells me that my original equation, x squared plus y squared equals 9, and both of those, x equals positive 3 x equals -3. All, not x, r. Oh my gosh, nobody called me on it. You guys got to call me on my nonsense. I've been talking all day. R equals 3, r equals -3. All three of those equations are going to plot the same graph. In other words, all of those equations are equivalent equations. They produce the same results. What shape do we think they produce? Any guesses? Circle. Yeah, those are a circle with radius 3 centered at the origin. Yeah. Yeah, this is just a circle. And it's much prettier in polar form, r equals a number, than x squared plus y squared equals a radius squared. Things that form closed curves tend to look prettier when you write them in polar. Some of us look like we've checked out for the weekend. Frowny face. Questions before we try another one? Give me a couple more minutes, just a couple. I'm going to take that as a no questions, and we will do another example. We have the equation x squared plus y squared equals 6y. We want to write it in polar form. So I'm lazy as a mathematician. If I can avoid doing complicated math, I'm going to. I'm going to scroll up to our last example because the left side of that equation looks familiar. We just dealt with x squared plus y squared. If I scroll back up and I look at what I just did, I'm going to circle it in blue. We started with x squared y squared on the left. We ended with r squared after we simplified. Right side didn't change, 9 and 9, yeah? But we replaced the x and y with r cos r sine. When we squared it, we ended up with that Pythagorean identity, and just the r squared stuck around. This tells me that x squared plus y squared is equal to r squared. That's the Pythagorean theorem for a right triangle. X squared plus y squared should equal the hypotenuse, r squared. I'm going to save myself a lot of trouble knowing that. Anytime I see x squared plus y squared, I know that it's equal to r squared. I don't have to go through that whole ugly simplification. I recognize that pattern. Which means on your homework and your tests, if you recognize that, you don't have to do all the algebra to get to it. Yeah? So the left, when I do my substitution, is r squared. What happens to the right? 6 times, and y becomes r sine theta. Not too scary. The question is, where do we go? I've substituted. It's as simple as it's going to get. My last step is to solve for r. I've got r on both sides of the equation. I want you to take about 60 seconds. Quickly discuss in your small groups. What's the next step if I want to get R by itself? Talk to your neighbors. I have wet dog syndrome today. My nose is so ready. All right, Jennifer. Suggestions on what I should do? Divide. What am I dividing by? R. So I saw that on somebody else's quiz last week. Yeah. If we were trying to get rid of numbers, it's okay to divide by numbers. When you divide by variables, you eliminate one of the possible solutions. So, I mean, you're right. Technically, you can. You can divide both sides by anything. But you're eliminating one of the possible values of R when you do that. So my recommendation is don't do that, because you're almost always going to lose the 0 and the 180 solutions, the x-axis solutions. If I can't divide and I need the r's on the same side, what else could I do? Yeah. No, what was it, Liliana? Give it to me. Square it? We could. It doesn't hurt anything, but it also doesn't help, because then we're just going to have an r to the 4th and an r squared. So not wrong, but not helpful. And that's okay, right? Trial and error. Another suggestion. We can't run away from things that are hard. Sometimes life is hard. You've done this before, Math 2, when you had equations with x's and y's. You want to get both variables on the same side of the equation. How do you do that? It's positive. Negative, yeah, subtract it. Exactly, yeah, subtract it from both sides. 6r sine theta minus 6r sine theta is 0, right? Anything minus itself is nothing. This side becomes 0. The left side is now a little bit uglier. I have r squared minus 6r sine theta equals 0. And when I see squareds floating around, I start thinking about things like factoring. Is there something that I can factor out of both of those terms? What do they have in common? What shows up in both terms? R, perfect, yeah. Let's pull an R out and then look at what's left over. If I take an R out of r squared, what am I left with? An R, yeah, perfect. If I take an R out of 6r sine theta, what am I left with? 6 sine theta, yeah, 6 sine theta. That's perfect. That's less scary, because now I have single powers of r instead of r squared. And I know that I have my 0 product property. If I have something times something equals 0, one of those somethings has to be 0. This gives me 2 equations. First thing equals 0, or second thing equals 0. One of those has already been solved for r. Yay. Second one isn't. It's r minus something equals 0, so I got to add that thing to both sides. So I'm going to add that 6 sine theta, which is going to give me r equals 6 sine theta. Unlike the last example where we got r equals 3 and r equals -3, and those are clearly equivalent, these two equations are not equivalent. One of them matches up with the one we started with, one of them does not. In polar form, remember that r measures the distance from the origin. If r is 0, where am I sitting on the coordinate plane? In the middle, at the origin, yeah. There's no distance from the origin. I'm right at the origin. This is a single point at 0, 0, which is not helpful. This is not a practical solution. Because I know, looking at my Cartesian equation, x squared plus y squared equals 6y, that's not a point. That's a curve. I don't know what kind of curve, but I know it's not a point. If it were a point, it would just be a number equals a number. That's not helpful. So the answer is the second guy. X squared plus y squared equals 6y in Cartesian is equivalent to r squared equals 6 sine theta in polar. And next week, we're going to look at the graphs of those and see how they match up. That's what we're going to do on Monday. Yeah? Substitute, simplify, solve for r. Yeah? Separately, they're all skills you have. Now you just got to put them together in sequence. Yeah? Okay. So, question is, what happens when we try to go backwards? Sometimes you encounter an equation in polar form and the shape isn't very obvious, but when you rewrite it in Cartesian, it's immediately obvious what it is. So sometimes we do actually want to go backwards. This process is going to look a little bit different than the last one did. Because we know when I'm trying to go from polar to Cartesian, my equations are uglier. R is the square root of x squared plus y squared. Blech. Theta is tan inverse of y over x. Blech. I don't want those things showing up in equations. So we're going to use the same set of equations that we just used and look for patterns in our polar equation. So the first step is pattern matching. So if you see an r cos theta or an r squared cos theta squared, what does r cos theta become? X, yeah. So if you see an r squared cos theta squared, that's an x squared. An r cubed cos theta cubed, that's an x cubed, right? You see r cos theta in any of its variations floating around, that's an x. If you see an r sine theta floating around, is y, yeah? And we know that if we see r squared by itself, that's x squared plus y squared. So we're looking to see if any of these things on the left show up in our equation so we can make the replacement. If they're not there, we're looking to see if we can do some algebra or some trig substitutions to massage it into forms that show up here. Because once I have these things in my equation, I can replace them with x's and y's. And that's way easier than dealing with the square root of x squared plus y squared and tan inverse floating around. Yeah? So after you pattern match, the next step is you're going to substitute, just like we did. Once you know what this thing is equal to, plug it into the equation. Any guess what comes after substitute? Simplify, yeah, it was the next step in the last process. Except here it's our last. And the reason it's our last is that when we take equations that are originally in polar form and we try to put them in Cartesian, oftentimes they're not going to be pretty when we do y equals some stuff. And so just simplify it so it's not a hot mess. Group all the like terms together. Yeah. Reduce anything that can be reduced, and then leave it. Yeah. There is no need to solve. So look for patterns, make the substitution, do a little bit of algebra magic to make it pretty. We'll do an example. Oops, that's not what I meant to click. Good idea. All right, so we want to take the equation r equals 2 secant theta, write it in Cartesian form. I'm looking for patterns, r cos theta, r sine theta, x squared plus y squared. Do I see them? No, frowny face. So what I'm going to do is I'm going to look really hard at that trig function that's there. Secant is 1 over another trig function. Secant is 1 over what? Cosine, yeah. This is 1 over cos. So let's make that replacement. Let's do that substitution and see if that helps us. So we get r equals 2 over cos theta. Replace secant with over cos. So 2 over cos theta. Ooh, I don't like things in fractions. I'm going to multiply both sides by that cosine so it gets it out of the denominator. Those guys cancel. On the left, I have an r times a cosine theta. What do I have left on the right side of that equation? 2, yeah. I see something familiar in there. What is r times cosine theta? X. This is just the equation x equals 2. What kind of graph does that make? Close, but not this kind. This kind, yeah, it makes a straight line, vertical. All of the coordinates for the x value are 2. Y can be anything. Yeah, good. All right, while you're packing up, you have Delta Math this weekend. Practice graphing points in polar form. Practice moving between polar and a Cartesian. When I see you on Monday, we're going to start looking at graphs and comparing polar and Cartesian equations and how those graphs look. Again, fidget toys, bananas, if you want them, please take them. Please. I no longer want them here.